So this will be section 4.3, and it's kind of just a continuation really of section 4.1. In section 4.1 we did probabilities, and in order to get the denominator of the fraction for our probabilities, we had to envision a sample space. Like we did probabilities, what is the probability of selecting a heart from a deck of cards. We did probabilities like that. And to do this, we kind of had, two numbers to come up with. We had a number for the numerator and a number for the denominator. And in all the card problems, our denominators were 52 because a deck of cards had 52 cards. And then to get the numerator, we looked through the all the possible cards and we figured out how many of them fit the characteristic, and we put that number in the numerator. In this case, there's 13 cards. So there's two numbers that are important when we do probabilities, the number for the numerator and the number from the denominator. Each of the numbers isn't particularly hard to get if you can have a sample space of all the different possible outcomes for an experiment sitting in front of you. In this section, we're going to be doing slightly more complicated, I'll call them experiments, or slightly more complicated probability problems. And we're going to need to be able to figure out a numerator and a denominator for a probability problem. And there's going to be some algebra or some strategies that we're going to do. There's two things that we're going to learn in this section. We're going to learn how to construct sample spaces really to help compute the numerator of a probability question, which is the top part of the fraction. And we're going to construct these sample spaces using something called a tree diagram that I'll get to in a little bit. They're kind of easy. Maybe the word seems imposing, but it's not so hard. So we're going to be constructing sample spaces with really the explicit purpose of answering probability questions, really getting the numerator part of the probability questions. We're also going to want to figure out what the denominator is for our probability questions, and to help figure out the denominator, for probability questions, we will use something called the counting principle. So there's two big I guess he's not your friend, principle. So principle, PLE, principle. So there's two big concepts in this section. They're really interrelated. The beginning of the section, we learn how to just use the counting principle kind of generically, not in the world of probability questions. And then we'll we'll take what we learned from the counting principle and we'll learn how to construct tree diagrams, and then we'll kind of use the two together. We'll use the counting principle to figure out denominators for probability questions, and we'll use tree diagrams to help us get the numerator. So there's two big concepts, and the reason each of the concepts, the tree diagrams is to create sample spaces for numerators. The counting principle is to figure out what number goes in the denominator of a probability question. And at first, we'll kind of baby step it using the counting principle. We'll do some non-probability questions for the counting principle just to get practiced with it, and then we'll use it to figure out denominators of fractions and probability questions. So the title of this section is Tree Diagrams and the Counting Principle, because tree diagrams help us create sample spaces to get the numerator for probability questions. The counting principle helps us get the denominator for probability questions. And at first, we're going to study the counting principle. It actually helps us get the denominator for probability questions, but we're going to do it in a more generic way, and hopefully it's not so bad. So if I read my work here, it says it's often necessary to know the total number of outcomes in a probability experiment, because that's the denominator for the probability question, any probability question. The counting principle is a formula that allows us to determine the number of possible outcomes, the number that goes in the denominator of a probability question, without actually having to create the sample space I need to get for the numerator. So this is a definition of the counting principle. I don't really ever test on definitions, and they're kind of even awkward for me to write, so I imagine I stole this somewhere from the internet. And then on the next page, I'll show you what I mean in terms of what the counting principle is, and I'll try to tie that together to this definition. So it says the counting principle: if an experiment can be performed m distinct ways, if a first experiment can be performed m distinct ways, and a second experiment can be performed n distinct ways, then the two experiments in that specific order, m first and n second, can be performed m times n distinct ways. That's a mouthful, and it doesn't really mean anything, probably, to somebody that hasn't studied counting or probability before. So let me do an example to help us understand the counting principle. So I'm going to do an example. I'm going to use the counting principle to find the number of possible outcomes for these two. I call these things experiments, but this is, a very loosely defined experiment. So use the counting principle to find the number of possible outcomes for these two experiments. So my first experiment, which I'll call maybe, my first experiment is a coin being tossed, and the side that's face up is recorded. So experiment 1, I have to figure out how many possible outcomes it has. And the possible outcomes for experiment 1, when I flip a coin and I record the side that's up, there's going to be two different outcomes. It either can come up ahead or it can come up tail. So experiment 1 has two possible outcomes. So in the counting principle, if two experiments are performed one after another, to figure out how many different ways those experiments can be performed in succession, I need to know the number of outcomes possible for the first experiment. I've just figured that out. There's two outcomes for the first experiment. My second experiment is a dice is rolled and the number that is face up is recorded. Well, when a dice is rolled, the number that's face up, assuming it's a six-sided dice, the number that's face up can only be the numbers 1 through 6. So the number of possible outcomes for the second experiment is 6. The counting principle says if the first experiment can be performed m ways, in this case 2 ways, and the second experiment can be performed n distinct ways, in this case 6 ways, then the two experiments in that specific order can be performed m times n ways. So how many different outcomes are possible if I flip a coin and then roll a dice? Well, the counting principle says there's 2 ways for the first experiment. 2 things that can happen are 2 outcomes for the first experiment. There's 6 outcomes for the second experiment. So the counting principle says for this experiment combination, flipping a coin, writing down heads or tail, and then rolling a dice and writing the number that can come up. There's 12 different outcomes that are possible. So this is what the counting principle would tell me, that there are 12 different things that can happen if I flip a coin and then roll a dice. I had to adjust my window. And some of the things that could come up, like I could get a head first and roll the number 1. Or I could get a tail and roll the number 4. These are just 2 of the 12 examples. So there's 12 possible things that can come up. Now I know how many outcomes are doing in this test, doing experiment 1 followed by experiment 2. If it was a probability question, that number 12 is going to be a number that I'm going to use for a denominator. The next thing I want to introduce is constructing the sample space, constructing all the possible outcomes for this probability experiment, and I'm going to do this using a tree diagram. So a tree diagram is a way to organize multiple experiments to figure out all the different possible outcomes. So the next thing I'm going to do is I'm going to create a tree diagram to generate or create the sample space for these 2 experiments. And it should have elements. The counting principle says because experiment 1 had 2 possible outcomes, experiment 2 had 6 possible outcomes, doing experiment 1 followed by experiment 2 should generate 12 possible outcomes. And I'm going to create all 12 possible outcomes, and I'm going to call that example space. I'm going to do that using a tree. And the first thing I'm going to do is I'm going to make a sideways, I guess that's more like a less than sign. And my first experiment is flipping a coin. And when I flip that coin, there are 2 possible outcomes. It could come up a head, or it could come up a tail. I made 2 lines from my initial point because the first experiment had 2 possible outcomes. My second experiment is rolling a dice, and rolling a dice has 6 possible outcomes. From each of these coin flips, I'm going to make 6 lines in my less than sign because there's 6 different numbers that a dice could come up. At the ends of each of these numbers, I'm going to write the numbers 1 through 6, the 6 different numbers that could come up when I roll a dice. And now I'm simply going to follow every path. I'm going to follow the path from the beginning point to the head to the number 1, and I'm going to call that in my sample space the first element of my sample space. It's going to have 12 different elements. The first element of my sample space would be getting a head for the coin, and a 1 for the dice. If I take the second path from the beginning point through this head to the number 2, I'm going to get the second element in my sample space, which would be getting a head for my coin flip and then the number 2 on the dice. And then I'll do the third path that goes from the point through the head to the number 3, and that's going to represent getting a head and then the number 3, and then I'm going to follow it to the 4 and write a head and a 4. Ultimately, I need to find a path to every single number in this far right edge of my tree diagram. To get to the 5 here, I have to go head first, then 5 second. And then to get to this 6, I have to go head and then 6. So this is the first 6 elements in my sample space. I don't have a lot of room here, so I'm going to write the next elements under it. The next element I'm going to write is I'm going to figure out how to get to that 1 from the point here. I'm going to go through the tail and to this 1, and I'm going to say a tail followed by a 1 is another element in my sample space. And then I'm going to get to this 2. To get to that 2 from this point, I'm going to go tail and then 2. And then subsequently, I'm going to go tail then 3, tail then 4, tail then 5, and tail then 6. And those will be all 12 elements in my sample space. The counting principle told me how many elements were going to be in the sample space. And if I count it, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The counting principle tells me how many elements are in the sample space. Tree diagrams help me generate the specific sample space when I have experiments done successively. So that's the tree diagram, and that's the sample space for this problem. Let's do another kind of example before we jump into any kind of probability kind of questions. So another example of doing 2 experiments that don't feel like 2 experiments. So in this problem, 2 balls are going to be selected from a bag without replacement, and the bag, I can't say that word so well, this bag of balls, it has 1 red ball, 1 blue, 1 green, and 1 orange. And the experiments I'm going to do, experiment 1 is just to draw 1 ball from the bag, and without replacement means don't put it back in. So for this experiment 1, there's 4 different balls I could get. So the number of outcomes for experiment 1 is going to be 4. Experiment 2 is going to be to draw a second ball from the bag, but I'm assuming that I'm doing it second, so already one of these balls is gone. So I don't know which ball has been taken out on the first experiment, but I do know if I take 1 ball from a bag that has 4 balls, that there's only 3 possible outcomes from experiment 2. I could get any of the 3 balls that are remaining. So the counting principle will tell me the number of ways that I could do experiment 1 followed by experiment 2 is the 4 outcomes that are possible for experiment 1 times the 3 outcomes that are possible for experiment 2. The counting principle says there's 12 possible outcomes. When I do these 2, I'll call them loosely experiments. I draw 1 ball of the 4 from the bag, I don't put it back, and then I draw 1 ball from the bag that has 3 left. So there's 12 possible outcomes. That's what the counting principle tells me. Theoretically, can happen if I do this. Even though it didn't really define it as experiments, I have to think of it as experiments to use the counting principle. So that's all what I have on this sheet. Now let's do a tree diagram to create the sample space. So the next thing I'm going to want to do is I'm going to create a tree diagram to illustrate or to generate the 12 elements in the sample space. So when I do this, I start off with a V, or a less than sign. And the number of lines I need from this less than sign is the number of outcomes from experiment 1. So I'm going to need 4 lines radiating from my less than sign. So let me make 4 lines here. And this is my experiment 1. This is picking or selecting the first ball. And there's a red, blue, green, and orange ball in this. And for experiment 1, I can get red, I can get blue, I can get green, or I can get orange. From each one of these letters, because on experiment 2 there's 3 possible outcomes, I'm going to make kind of a 3-leveled less than sign. So from this red, I'm going to put 3 lines out from it. From this blue, I'm going to put 3 lines out from it. From the green, 3 lines. And from the orange, 3 lines. And each one of these, I have to put the possible outcomes. And for this first situation, if I picked a red marble or a red ball, then what's left is a blue, a green, and an orange. So at the end of these lines right here, I'm going to put the balls that would be left in a bag if you took the red out. If you took the red out, you'd still have the blue in, you'd still have the green in, and you'd still have the orange in. If on your first chance you took the blue out, then you'd still have the red, the green, and the orange. So at the end of this, I'm going to write a red, green, and orange. If you took the green out, then you're still left with the red, the blue, or the orange, and I'm going to write that at the end here. And if you took the orange out, you'd have the red, blue, and green left, and I'd write that at the end here. And now I need to figure out how to get to each letter in the far right-hand column. To get to this letter, the easiest way, the only way to get there is to do red first and blue second. So part of my sample space is going to have getting a red first and a blue second. To get to that green, I need to have a red first and a green second. I'm going to mark it out once I've used it so I don't need to use it again. To get to that orange, I need to have a red first and an orange second. So I have 3 elements in my sample space. To get to that red, it's a blue first and a red second. I'm going to mark it out with a cross because I've gotten there. To get to this green, it's a blue first and a green second. Mark it out because I've gotten there. To get to this orange, it's a blue first and an orange second. I'm already out of space again, so I'm going to go under. To get to that red, it's a green first and a red second. To get to that blue, it's a green first and a blue second. To get to that orange, it's a green first and an orange second. To get to this red, it's an orange first and a red second. To get to this blue, it's an orange first and a blue second. And to get to that green, it's an orange first and a green second. So this is a kind of an abbreviated sample space. The counting principle, when we used it, told there'd be 12 possible elements in my sample space. If I count these up, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outcomes, which matches perfectly. So they work hand in hand. The counting principle tells you how many elements are in your sample space. That's the number that we use for denominators of probability questions. And tree diagrams help us generate all the individual elements of a sample space. Now we're stuck doing a probability question. So for this particular problem, let's do a probability question. We want to do the probability from this experiment of picking 2 balls, one after another, without replacing the first ball. What's the probability that I pick an orange ball? Ugh. So to do a probability question, I'm going to form a fraction. The denominator is the number of elements in the sample space. The counting principle tells me there's 12 elements in the sample space, so I'm going to put a 12 in the denominator. So the counting principle helps me get the denominator. It doesn't do a heck of a lot of good for the numerator. The numerator, I need to look through my sample space that I created and count all the different ones that have orange balls. So there's my sample space. Let me go through the sample space. Red and blue, red and green, red and orange, that has an orange ball. Blue and red, blue and green, blue and orange, that has an orange. Green and red, green and blue, green and orange, orange and red, orange and blue, orange and green. So all the ones that I just highlighted have orange balls. This is going to be the number that goes from the numerator. The desired characteristic is getting an orange ball. There's 1, 2, 3, 4, 5, 6 elements of the 12 in the sample space that have an orange ball. So the numerator of my fraction is going to be 6. And generally, when we do probability, we reduce. And I'd say the probability that I get an orange ball from this particular experiment of picking one ball, not putting it back, then picking another ball is 50%, or 1 in 2. All right, let's do another counting principle problem, and a very similar counting principle problem, but I'm going to change a word. So 2 balls are selected with replacement from a bag that contains 1 red, 1 blue, 1 green, and 1 orange ball. Use the counting principle to determine the number of points in the sample space. Well, the first experiment is selecting the first ball, and it's from this bag that has 4 different balls in it. So for experiment 1, it's just selecting the first ball. And just like the last example, this bag has 4 balls in it, so there's 4 possible outcomes for the first experiment. The second experiment, again, is selecting the second ball. But this word that says with replacement, that tells me that after I put the first ball, after I take the first ball out, I put it back. The difference between the last problem, I used the word without replacement. In this, I took the first ball out and didn't put it back, so my bag went from 4 balls to 3 balls. In this next example, it says 2 balls are being selected with replacement. This implies that there's 4 balls available for the first experiment. You're going to take that ball out, look at it, write its color down, and then you're going to put it back in. You're going to replace it back in the bag. For the second ball, there's still going to be all 4 to choose from. There's still going to be all 4 different balls because you're putting back the first ball. So the counting principle says if you take the number of outcomes from experiment 1, which is 4, times the number of outcomes from experiment 2, that there's going to be 16 different outcomes of picking balls in this from this bag if you put a ball back as opposed to not putting it back. I didn't do a create a sample space here because sample spaces that have 16 are kind of a nuisance to create. But if I wanted to create a sample space, I'd have to do this. I'd have to create a less than sign that has 4 branches coming out of it because there's 4 outcomes for the first experiment. I could get a red, a blue, a green, or an orange. From each one of these, I'd have to have 4 more branches because the second experiment also has 4 different possibilities. And this would be a mess, but I could certainly do this if I had the patience to create the sample space. But the important thing is to know how to set it up. My first kind of less than sign has 4 branches coming out of it, and then each of the letters here will have 4 branches coming out of it, and then I would just write down each of the red, blue, green, and orange again, because each time you could get any of the 4 because you're putting the ball back in, and then you can create the sample space. It would have 16 elements. That's going to take a long time, longer than we need to do. Generally, I don't create sample spaces that are so big. Here's another counting principle problem that doesn't feel like it's an experiment problem, but yet we can consider it an experiment problem. So Joe has 7 shirts, 4 pairs of pants, and 2 pairs of shoes. So let me write this down. He has 7 shirts, 4 pants, and 2 shoes. He needs to make an outfit containing 1 of each item. How many different outfits are possible? Well, we wouldn't generally consider picking, a shirt, a pair of pants, and a shoe an experiment. But this is how we're going to have to think of this. We're going to have to think of picking a shirt as experiment 1. So he's going to pick one of his 7 shirts. And then picking a pair of pants is going to be experiment 2. And then picking a shoe is going to be experiment 3. So if Joe wears his gray khakis and his white button-up shirt and his black shoes, that's going to be different if he wears the same shirt and pants and wears his Vans shoes or something. So changing one of the 3 elements, the shirt, pants, or shoes, it makes it a different outfit. Even if you have the same pants and shirts on, if you have different shoes, we'll count those as a different outfit. So to figure out how many different outfits are possible, I'm going to consider experiment 1, selecting a shirt. There's 7 different possible outcomes for this experiment because there's 7 different shirts. Experiment 2 is selecting a pair of pants. There's 4 different possible outcomes for this experiment because he has 4 different pairs of pants. Experiment 3 is selecting a pair of shoes. There's 2 outcomes for that experiment because there's 2 different pairs of shoes. And then the counting principle will extend. If I do 3 experiments in a row, if I know the number of ways outcomes for each experiment, if I just multiply those numbers together, that's going to be the number of outcomes for those experiments done in that order. So picking a shirt, a pant, and a pair of shoes creates an outfit. There's going to be 56 outfits that Joe will have. Granted, some of them will be very subtly different. You know, they might have the same shirt, the same shoes, but a different pair of pants, and we'll call that a different outfit. All right, I don't like problem 1 so much, but let's jump into some homework. We're going to use the counting principle to try to get good with it. So problem 1 says 2 dates are selected at random from the 365 days of the year. So what might happen is I might put on individual pieces of paper, maybe January 1, January 2, all the way up to December 31st. So I'm going to take 365, essentially, I'll think of this way, slips of paper and put them in a hat, and I'll pick out 2 dates. Experiment 1 is going to be selecting whatever day that I pick out of the hat. And experiment 2, because we're picking 2 days, is going to be selecting the second day. I'm going to answer some how many questions using the counting principle in a second here. The first question is asked, use the counting principle to determine the number of possible outcomes if the dates are selected with replacement. So in this hat that has 365 slips of paper with the dates, that's kind of how I'm imagining this just to make it easier for me to conceptualize. The first experiment is selecting the first day. There's 365 different days in the year, unless it's a leap year. So there's 365 possible outcomes for the first experiment. The with replacement means if I picked March 14th as my date, I'm putting it back in, and the second experiment still has that date to choose from. There's going to be 365 choices for the second experiment. So the number of possible outcomes here would be 365 ways the first experiment can be performed, or outcomes from the first experiment, times the 365 possible outcomes from the second experiment. And when I multiply these together, 365 times 365, I get 133,225 different possible outcomes of selecting 2 dates if I put the first date back. For part B, it's the same 2 experiments. First experiment is selecting the first date. The second experiment is selecting the second date. The difference between question A and question B is the word with replacement and without replacement. When I have the word without replacement, that's going to impact experiment 2, but not experiment 1. So this was for part A of number 1. Off to the side here, I'm going to get the numbers for part B. For part B, experiment 1 is selecting any one of the 365 days. There's going to be 365 possible outcomes for that experiment. When I go to do experiment 2 for part B, I'm assuming whichever date that I picked for experiment 1 that I don't put it back in so I can't select it again. So there's one less slip of paper in my hat. There's only 364 possible outcomes for experiment 2. So when I go to answer the how many question, there's 365 possible outcomes for experiment 1. There's 364 outcomes for experiment 2. And when I multiply those, you get 132,860, I think. So 365 times 364, perfect. Let's do a couple more counting principle problems, and then we'll move on to some tree diagram problems. So your problem 3, hopefully you can do it, because just like the example that I did, and for an answer to problem 3, I have the number 60 written down for an answer. I'm going to do my problem 4. Shannon is going to purchase a new car. The car has 5 exterior choices, 2 interior choices, and 2 engine options. How many cars are possible? I'm going to call experiment 1, picking the exterior color. And there's 5 different outcomes from that experiment. I'm going to call experiment 2, picking the interior color. And there's 2 different possible outcomes for that. In experiment 3, I'm going to say it's going to be picking an engine, and there's 2 possible outcomes for that. The counting principle says if I do 3 successive experiments, and I know the number of outcomes for each experiment, that I can just multiply those numbers together to get the number of possible outcomes, or in this case, how many different cars. And again, if I have a red car with a gray interior and a 6-cylinder engine, that's different than having a red car with a beige interior and a 6-cylinder engine. It has one difference, it's counted as a different car, and that will give me 20 different outcomes. Let's work through 5 together. So in problem 5, I have a remote control that has the digits 0 through 9. I'm going to press 2 buttons, the first button and then a second button. And let me define this and help me answer probability questions by creating an experiment. So experiment 1 is going to be selecting whatever button I press first. My first, I'll call it a digit. I can pick any one of the numbers from 0 through 9. In my experiment 2 is going to be selecting, that's really spelled nicely, selecting the second digit. For experiment 1, I can get any number between 0 and 9. And this is tricky because there's 10 numbers there. The numbers 1 through 9 and the number 0, there's 10 possible outcomes for experiment 1. For part A, because the same button can be pressed twice, regardless of what button I press on this first experiment, all 10 buttons are available for my second experiment, so there's 10 possible outcomes for the second experiment. The counting principle says, since there's 10 possible outcomes for the first experiment and 10 possible outcomes for the second experiment, if I multiply those together, that's going to be the total number of outcomes of those experiments performed in order. For part B, experiment 1 is still selecting the first digit. Experiment 2 is still selecting the second number or the second digit. And let me figure out the numbers that I need for 5B. For 5B, the difference between 5A and 5B, it says the same button can't be pressed twice. For selecting the first digit, I can pick any of the 10 digits. But when I go to do part B, selecting the second digit, once I pick a number, I'm not allowed to pick it again. So regardless of the number I pick, there's one fewer number to pick for the second choice. So there's only 9 choices for for the second experiment. And for part B, the number of outcomes of this possible order of events here is going to be 90, because I can't pick the same value twice. So my answer to part B is going to be 90. Why don't you give 7 a go? I have an answer written down for 7, and hopefully you might be able to figure out how to do it. I wrote 9 for my answer. I'm going to go through and do 8. So girls' ice skates come with the following options. They have 1, 2, 3, 4, 5 colors, and 1, 2, 3, 4, 5 sizes, and they have extras of tassels, striped laces, and bells. They have three extras. So I'm going to have 3 experiments here, and I'm going to find out how many different kinds of skates are possible, having a color, a size, and an extra. I'm assuming you're going to have one of each. So how many possible skates are possible picking one color, one size, and one extra? So experiment 1 is selecting a color. There's 5 possible outcomes for experiment 1. Experiment 2 is selecting a size. There's 5 possible outcomes for experiment 2. And experiment 3 is selecting an extra, and there's 3 possible outcomes for selecting experiment 3. The number of possible skates are going to be found by taking the number of outcomes of each of the experiments. 5 times 5 is 25, times 3 is 75. So for this category, these options, if you're forced to pick one color, one size, and one extra, there's 75 different skates that are possible. And again, just having one difference. Having a white size 5 skate with a tassel is different than having a white size 5 skate with a bell. I'll go through number 9 with you because it's kind of a mess. So a state issues license plates consisting of numbers, letters, and numbers. There are 26 letters that may be repeated. There are 10 digits, and the digits may be repeated. How many possible license plates can be issued with 2 letters followed by 3 numbers? So experiment 1 is going to be getting the first letter. So how about first letter? Experiment 2 is getting the second letter. And then experiment 3 is going to be getting the first number. Experiment 4 is getting the second number. And experiment 5 is getting the third number. So I need to get 2 letters and 3 numbers. Now I need to find the number of outcomes for each. So let's go to experiment 1. Well, there's 26 letters, and letters may be repeated. So for the first letter, I have 26 letters to choose from. Because letters can be repeated, for the second letter, I have 26 letters that can be chosen from. There's 10 digits. The numbers 1 through 9 plus 0 gives me 10 digits. For the first number, I have all 10 digits, 1 through 9 plus the number of 0 to choose from. And because digits can be repeated, for the second digit, I still have all 10, and the third, I have all 10. So if I multiply these together, first letter times second letter times first number times second number times third number, I'll get the number of possible license plates by doing these 5 selections, considering each as an experiment. So first letter 26, second letter 26, first number, second number, and third number 10, 10, and 10. If I multiply all these together, so 26 times 26 times 10 times 10 times 10, I get there are 676,000 different license plates that have 2 letters followed by 3 numbers, assuming you're allowed to repeat letters and repeat numbers, and that's where we'll leave that at. Let's move on to 11 and 12. This is the same kind of problem. I'll do number 12. You can try number 11. For number 11, I came up with 900. I don't feel my answer for number 11 that can possibly be right. This is, let me do number 11 with you real quickly, because when I look at my answer, it has nothing to do with this. So Burger King has 4 types of burgers, 5 types of beverages, and 3 types of dessert. If a meal consists of 1 burger, 1 beverage, and 1 dessert, how many possible meals are there? So experiment 1 is picking a burger. there's 4 different outcomes for it. Experiment 2 is picking a drink or a beverage, and there's 5 different outcomes for it. Experiment 3 is picking a dessert, and there are 3 different outcomes for it. So how many meals are possible? It's the number of outcomes of experiment 1 times the number of outcomes of experiment 2, find the numbers of outcomes of experiment 3. Experiment 1 is picking a burger, there's 4 possible outcomes. Experiment 2 is picking a beverage, there's 5 possible outcomes. Experiment 3 is picking a dessert, there's 3 possible outcomes. There's going to be 4 times 5 times 3, which is 60 different meals that you can get at Burger Queen. So eventually, I stopped writing down experiment 1, experiment 2, experiment 3, because it feels so labor intensive to do that. So let's walk through problem 13 and maybe not write down the experiments. Maybe maybe try to speed this up a little bit. So Rita's ordering a birthday cake for a friend. There are 5 cake flavors and 4 frosting flavors. Experiment 1 is going to be selecting a cake flavor. And the number of outcomes from experiment 1 is the 5. He can select any of the 5 cake flavors. Experiment 2 is selecting a frosting flavor. And there's 4 different outcomes for experiment 2. How many outcomes are there for doing experiment 1, picking a cake flavor, times experiment 2 for picking a frosting flavor? That's like getting a white cake with strawberry frosting or a chocolate cake with chocolate frosting. There's going to be 20 different outcomes, or 20 different birthday cakes that are possible. Now I'm going to do problem 14 because you need problem 14 to do problem 15. So a car license plate consists of 3 letters followed by 3 numbers. So my experiment 1 is going to be picking the first letter. My experiment 2 is going to be picking the second letter. And my experiment 3 is going to be picking the third letter. Experiment 4 is going to be picking the first number. Experiment 5 is going to be picking the second number. And experiment 6 is going to be picking the third number. So there's kind of 6 experiments. I pick the first 3 letters followed by the first 3 numbers. How many license plates are possible if there's no restrictions, meaning letters and numbers can be repeated? Well, I should know there's 26 different outcomes for the first letter because there's 26 letters to choose from. Since there's no restrictions, I can pick all 26 letters for each of my experiments of picking a letter. For the digits, there's the numbers 1 through 9 plus 0. That's an available digit. There's 10 digits available, and it doesn't say anything about having any restrictions. So for each of the numbers, all 10 digits are available. The number of outcomes that are going to be possible for this license plate, the number of license plates that are possible, I'll get by multiplying all those numbers together. There's going to be 17,576,000 possible license plates. Let us work on problem 15 together real quickly here. So in problem 15, we want to do create license plates, and how many license plates are possible that have 2 letters followed by 4 numbers, but there's no other restrictions. So there's 6 experiments. Experiment 1 is picking the first letter. There's 2 letters. Experiment 2 is going to be picking the second letter. Done with the letters, experiment 3 is going to be picking the first number. Experiment 4, the second number. Experiment 5, the third number. And experiment 6, the fourth number. So there's 2 letters and 4 numbers. There's quote-unquote 6 different experiments. There's no restrictions, meaning I can use the same letter more than once. I could use the same number more than once. For the first letter, there's all 26 letters in the alphabet to choose from. Since there's no restrictions on the second letter, I'm assuming I could use all 26 letters for the second. For the number, The first number, I could use the numbers 1 through 9 plus 0, so there's 10 digits to choose from. There's no restrictions, so I'm assuming I could have 8888 for my 4 numbers. I'm allowed to repeat, so there's going to be 10 numbers to choose from for each number. And if I multiply these out right, I think you get 676,000. I get actually 6,760,000 possible license plates with these having 2 letters followed by 4 numbers without any other restrictions. So that would be the answer to 15. Might as well work on 17 together. If you want to pause and give it a go, the answer I have written down for problem 17 is 78,624,000. So, standard New York license plate has 3 letters followed by 4 digits. So there's going to be 7 experiments, picking letter 1, letter 2, letter 3, number 1, number 2, number 3, and number 4. How many license plates are possible if neither the digits nor the letters can be repeated? So let me work on this, write it down. Experiment 1 is getting letter 1. Experiment 2 is getting letter 2. Experiment 3 is getting letter 3. Experiment 4 is getting number 1. Experiment 5 is getting number 2. Experiment 6 is getting number 3. And the last experiment is getting the 4th number. So, it says neither the digits nor the letters can be repeated, meaning once I pick a letter, I can't use it again. For the first letter, I have all 26 letters in the alphabet available, but once I use a letter, I'm assuming I'm not allowed to repeat it. So when I go to pick for my second letter, whichever letter was being used first, I can't use, so I need to go down by 1. There's only going to be 25 letters for the second letter. And for the third letter, I can't use either of the first 2 letters, so I'm losing 2 letters, and there's only 24 to choose from. For the first number, I can choose any of the numbers between 1 and 9 and 0, so there's 10 numbers to choose from. And then I'm not allowed to repeat it, so whichever number I pick first, I'm not allowed to repeat. So I'm going to go and have 1 fewer number for the second number. I'm going to have 2 numbers used up. By the time I go to the third number, I'll have 1 fewer number and then 1 fewer number. When you can't repeat letters or can't repeat numbers, you increment down each time. So let's work this out. 26 times 25 times 24 times 10 times 9 times 8 times 7. And I get that lovely 78,624,000 different license plates. So this will be the last problem for this part, and then I'll do a second part to the video just to make it not any longer than it is. So you are assigned a computer-generated 4-digit password for your new voicemail. If the digits can be repeated, how many passwords are possible? So I'll get it started for you. Your experiments are picking the first number for your 4-digit, assuming it's all numbered, then you have a 4-numbered password. So you have to pick the first number. You have to pick the second number for your password. You have to pick the third number for your password as the third experiment. The fourth experiment is picking the 4th number. You have to decide how many different digits are possible for each. Put numbers in there, multiply them together. If you do it right, I believe the answer to number 19 is there's going to be 10,000 different passwords that are possible. You know, one of them might be like 0013. Another one might be 9692. So there's 10,000 different ones like that. 0000 would be an acceptable password because you're allowed to repeat digits. All right, so let's stop this and do a part 2. Part 2 is going to be more doing the trees and doing probability questions.